He comes all the way from Catalonia. He's going to talk about how about scaling Ethereum. Please make him feel very, very welcome. Put your hands together for Jordi Baylina.
Thank you very much. It's a huge pleasure to be here in my city where I was born. So, well, I'm going to explain here a little bit how we are in Polygon. We are scaling Ethereum. My presentation will have like 3 parts. The first, I'm going to give a slide of the current state of the Ethereum zkEVM and explain a little bit the progress. Then mainly I'm going to work about the Polygon 2.0 that was announced last 2 weeks ago, I think, but we're announcing it. And then I'm going to explain let's say the short-term and mid-term work that we are doing in the Polygon zkEVM, more the technical details in what we are building. There are questions. I think this is the QR code. The presentation is only 20 minutes, and I think that 5 minutes is for questions. So I'm going to go a little bit fast, so we have time for questions at the end. So let's start. This is the current stage of the Ethereum network, of the Ethereum zkEVM. We decided not to go crazy. I mean, we are not in a race with anybody of the TVL. What we are doing mainly is we are onboarding a lot of projects. We are working together with them. We are increasing the transactions, I would say, in a healthy way. I mean, no tokens, no airdrops, no stakings, and no crazy things. We are trying to do the things the right way. We are working a lot in fixing, fine-tuning, improving, and this is the way that we like to work in Polygon. But even that, these are the numbers. Still a lot of, it's a lot of things that are happening currently in the zkEVM. Okay, let's talk a little bit about the Polygon 2.0. I mean, at the end, what we are trying to build at Polygon is a long-term strategy, but it's a strategy that's based very much in the zk technology. What we are trying to build at the end is, we can call it a constellation of rollups. It's a space where you can have rollups. We can have rollups that can be private rollups, can be public rollups. Some of the rollups may have a centralized sequencer, others may have a decentralized sequencer with different parameters. Some of them may be like Validium kind. Some of them are going to have the data on chain, so are going to be normal rollups. And the idea is that all these rollups there's going to be a kind of a composability between these rollups. In order to have this, so that from the user perspective, at the end, they see like as a single network. Okay, that's the final idea. For that, we have a shared liquidity, so it's going to be a single bridge, which all the funds are going to be there. That means that it's going to be easy to transfer funds between one rollup and the other rollup. One of the big differences, and this is one of the differences between Optimistic and zk, is that in zk we have instant final validity. That means when you send the proof, you know that this state is valid, so that this is very important when you are transferring funds between rollups and when you are moving between layer 2s. Okay, and the idea here is to have a single. Here the idea is to have so each rollup may have like a single proof that is proving the chain, but the idea is that the full ecosystem is going to be a single proof, or it's going to be a single proof that's going to be decentralized. That's going to aggregate all the rollups. Okay, so the idea is with a single proof we can prove all the rollups that are in the Polygon 2.0, okay? And this rollup, this proof can be generated, we are thinking in terms of seconds, maybe it's half a minute, 1 minute, or something like that. So it's going to be like a clock. Every clock, there's going to be a transfer between the rollups, okay? The coordination, so that the generation of this proof is going to be coordinated with a specific consensus layer that's going to coordinate this rollup. Okay, and the other thing that we announced is that in this network, it's going to be many networks with different parameters. But one of the things that we are proposing to do, it's moving the current Polygon PoS to a rollup. This is a long term. Probably it's going to be the last the last network that's going to be in here. We need first to build this constellation and have many rollups there. But the idea is that for the people that's building on POS, they will have this add-on, this advantage that they will also be part of these Polygon ecosystems. This is very interesting because you have, for example, private rollups that they can communicate with public rollups, private between private, public between public. There is a lot of combinations, a lot of interesting ideas for these different rollups. Okay. Of course, going to be some centralized sequencers, but the idea is that also it can be some decentralized sequencers. Sequencers, for the people that don't know, is the actor, the role of just getting transactions and ordering, sorting. They are not executing the transactions, but they are, okay, we decide that these are the transactions that we are going to execute next. These are the next one, okay? So it needs to be somebody that decides who is. In a normal blockchain, this is the miner, and the miner is just changing, but in a centralized sequencer, there is a role that's saying that, okay? The idea is that, to add a consensus layer here. Actually, right now, there is a centralized sequencer is also a consensus layer. We can call it, let's say, a dictatorship consensus. Is whatever the centralized sequencer says, this is the consensus. So it's very easy consensus, probably the easiest one. But the idea is to substitute this idea, to substitute this decision that's taking the decentralized sequencer with a layer one that's deciding about these transactions. But they are not executing, and that's why it's scared. So they are just deciding about blobs. They are saying, okay, this data, this data, this data, and this data, when you process this data, you get a new state. Okay, and you prove this new state. Okay. Well, this is going to be built with a Polygon stack. So the idea is to have this more from the software perspective, but the idea is to have a single, so having a prover. Right now we are working in Plonky 3. Plonky 3 is, right now we are working Plonky 2, that's very much based on the Goldilocks, okay, at least the ideas. Plonky 3 it goes to even a smaller prime number, and it's at 32 bits. This fits very good in GPUs and vectorization things, and it's a specific team that's working in having a single proven system that's important. We have the zkEVM, so that's the zkEVM. It's going to be zkEVM and Maiden. We have the client, so it's a team that's working with a single client, the bridge, staking hub, and Ethereum. Okay, but this stack is a single stack. So instead of having like many stacks, the idea is to try to have a single stack with the best functionalities of each guy. Okay. Okay, so here is a little bit the idea of the Polygon 2.0. So now I'm going to talk a little bit about what we are doing in the Polygon zkEVM. So as you know, we launched it on March. Well, a lot of work have been happening from there. A lot of, I would say, adjusting, fixing things, getting the things better. And but the planning we are going to do. I can announce now that we are going to do the first consensus or the first upgrade of the smart contracts very soon. Is what we call it the fork ID5. Here we are going to add mainly the push 0 opcode that's in there, and a couple of minor fixes. One of those is required to enable the forced transactions. It's a bug that we need to fix in there. Okay. The next step this is going to be probably happen in September, October. It's fork ID5. Here we are going to be probably a type 2 rollup. At least we are going to implement pairings. We already have pairings implemented internally. We are going to add SHA-256 and the exponentiation precompiled smart contract. With this, I mean, maybe there are some very strambotic smart contracts that would still pending, but we can consider that we are mainly a type 2 if we have these compiled, because with this 99.999% of applications is what they are using, and we are going to launch that September, October. Okay. Another thing that we are working on, this is very interesting. This is more, it's a better prover. Right now, the prover is a monolithic proof where you have, you prove. I mean, if you see the zkEVM, we are proving these transactions, but here we have we have some state machines that do arithmetic operations, some of them that do ketchup, but they do a fixed number of ketchups. Okay, this is the idea of the counters. And here the problem of this structure is that you don't use it very efficiently, because maybe there are some transactions that maybe you are using just half of the ketchups that you have in the proof. Okay, or sometimes you need more ketchups and then you cannot build the proof. Okay, and then maybe it's an operation transaction. Okay, so this has a little problem of the flexibility. So the idea here is to build a proof that each of the state machines can have different sizes. And not only that, even you can aggregate many of them. For example, if you have a lot of binary operations, you can take a lot of the binary operations, you can recursively, you generate this recursive proof, and at the end, you just join all the proof together. Here there is an interesting paper that we did in Polygon, in the research team in the Polygon, that's how to communicate between different degree parts of the proof, and we are extensively using in this new architecture. This is one of the topics that we're working a lot. Okay. So these are very much the advantages of the bad cops. We're also working in the PIL too. As you know, we built PIL to build all the arithmetization for the Polygon zkEVM. We are currently working with the PIL 2. This is a more, it's an extension of this language. I'm not going to go deep because we don't have much time, but here is, of course, we have bad cop support. The language is going to be a constructive language. Right now, PIL is just a list of constraints, and here you will be able to have like loops and conditions, very much like how Circum works. That you can build these constraints in a programmatic way, like a macro. Okay, so you can have. Right now we are not using it, but sometimes we have a external JavaScript program that's generating PIL. So the idea is to have this. We are trying to avoid these auxiliary programs and keep everything in PIL, so that's very easy to audit and to see how the arithmetization it looks like. Okay, more on constructive challenges. We have also challenges in PIL 1. We have some, let's say, high-level operations. For example, we have an instruction for doing lookups or for doing permutation checks or copy constraints. The idea of this PIL 2 is that these high-level constructions are built themselves in PIL. So the system is going to be more row-level, but it's going to be a library where you can do lookups. But if there is a new protocol, for example, for doing better range checks or for checking some weird things, the idea is that we will be able to build that on that, and then you will be able to have libraries where you have all these. Protocols embedded in there. Fixed columns. Right now we have external programs to put all the constants of all these the constant values of these fixed columns. We have a full programmatic way to include it here in the PIL. This is going to be very helpful, especially for auditing, and so you have everything in the same place. Maybe there is still some polynomial very specific that requires something outside, but here, because it's programmatic, you can generate it with this. Okay, you can access right now in PIL. You just access the current row or the next row. Here we have a system where you can access the previous row, the next row, or even 2 previous, 3 previous, and all that in a programmatic way. And here is this PIL also. Okay, you have the PIL, this is the constraints, but a lot of times when you build a proof, you need what we call the witness computation, okay? And then you need to give some hints, you need to give some information that you need to transfer to the witness, to the person, to the witness generation. So here we're adding the concept of hints also to build to pass to the witness. So you can have libraries in the witness generation that traits specific state machines of the specific libraries of the PIL that they work together and they generate. Okay, you can have a PIL for lookups, and then you have like a library for the witness computations that just fill the witness of the polynomial computations. Okay, but you need to pass information which polynomial is which when you are defining. Okay, so this is very technical, but this is very important because this will give a lot of improvement in the generation of this proof. Okay, the other part, more that we are working is very much in data compression. The idea is that right now we are putting the full transaction with the signature all together on chain. Okay, we are doing zero compression at this with the current version. The idea is that we can compress this. Okay? Give you here some hints. Well, this is a little bit how compression does. At the end, you can understand a compression file as a set of commands that's like printing information. So you can have, for example, a raw write. That's something you want to put some information that's not compressed. Okay. But here, things that you can do is, for example, one of the things that you can do is, for example, removing the signature. Removing the signatures. The idea is to substitute all the signatures of the transactions with a proof that there is one single, with a proof that all these signatures exist. Okay. The problem is, well, the problem or the difficulty or the challenge here is that you want to include this proof, this aggregated signature, if you want, in the data availability, and then you want to prove that in the prover. Okay, that means that in the prover you need to have pairings, for example, because you want this to be short in one side, because data availability, you don't want a big star here. You want to save in this form, but at the same time you want to be able to prove it. Because right now we already have pairings, this is perfectly possible. So we can aggregate that, put it in a elliptic curve kind proof, and then verify in another proof that aggregates other proofs. Reference to all that. Another thing that takes a lot of data is addresses. I mean, when you have a lot of addresses are random numbers. The idea is, of course, the first time that you are using an address, you will have to you will have to put the exact address, okay? But once you reuse this address, the idea is that instead of having this address, you just can put an index to previous address, okay? So you need to keep in the state of previous addresses, but you can perfectly do that, and here you save a lot of information, okay? Okay, here you have batches. The batches you create blobs, and the blobs, well, it's more the technical detail, and then you aggregate the blobs, and finally you have a single proof that aggregate everything, okay? Here, just with data compression, we expect 5x improvement in capacity. Just with the same data availability, we can compress the information 5x, okay? And the other thing is that with EIP 4844, that we expect this to happen by the end of this year, beginning of next year in the Ethereum Foundation. This will give another 10x on top of that. So when you join together, we expect to have a capacity of 50x by the beginning of the next year. Okay. Of course, to scale the system is not enough on the provers, on the prover part. You need to. This is like a car. You have a car, and you have so you have a car and you build an engine, but it's not enough to build a good engine. You need to build a good wheels. You need to have a good shape, and you need to build everything on the car. Okay, so we are working also in the synchronizer, in the databases, sequencer, and all this part. Just a few mention that one of the cool things of being a zkEVM is that we get, for example, the work from the Ethereum space for free. For example, the EIP 4337, the ERC 457 for the count abstraction. I mean, we didn't plan it to have a count abstraction in the zkEVM, but we already have it for free because we are EVM. If Ethereum have it, we have it. We just need to deploy the smart contracts without compiling in the Polygon zkEVM. We're working in decentralized sequencer, as I mentioned before. Security, I would say that the thing that I'm more focused is in the forced transactions. This is the thing that we want to enable as soon as possible. But here is well, a lot of course, it's always a work in progress in there. Okay. And yeah, this is a little bit of roadmap, and yeah, that's very much. I think I have 2 minutes for questions. Oh, just remove. Well, the question that I read is what's the cause of the variability, why the transactions are, the price of the transactions are different, depending what's, and here is very much is the biggest bottleneck is the data availability. Data availability, you need to pay the data availability. Here there are different strategies. One of the things that we are going to implement now in the next fork ID is that we are going to play with the effective gas price. So the idea is that the user will set up a gas price limit, but then the sequencer will be able to just charge a percentage of that. Okay, and with this we will adjust the difference between. So we are going to charge at the end the real cost, not the actual cost. Okay, right now it's a little bit messy because it depends many things, but with this new fork ID, this is one of the things that we expect that's going to be better, and especially for DeFi transactions, we expect reduction in the price. So transactions that are very, I would say, computing intensive and they have low data, like DeFi transactions, they are going to benefit very much on this. Okay, I think I'm running out of time, but I'm here outside available. If any of these questions want to ask me directly, I'm happy to answer to you. So I don't want to be out of time, so thank you very much.